So that since Pino already started with this, come to Prague. There's great merchandise for cryptographers. Okay, you haven't know. So this is joint work with Michal Koutsky, Karel Kral, and Veronika Slivová. We're all at the Computer Science Institute at Charles University in Prague. And I'll be telling you about some generalization of the lower bounds for ORAM that we saw. So, well, okay. So I'll assume that you are all exhausted, and I will go over the stuff. And if you don't understand anything, then it's my fault. So just ask me questions. My goal is to give you the main ideas of the paper, and then, I don't want to be very technical, just that you get the main points. And if you want, everything is written in the paper. It's online, and I can also explain it offline. So now, online ORAM. So what is the problem? We have some weak device and an untrusted server, right? And the device is implementing some RAM program. What does it mean? Well, there are some input operations that are coming to the device, and they're supposed to be implemented. And the issue is that the device doesn't have enough memory, right? So it needs to use the memory at the server. So whenever something comes, right, it has this structure. So it's, let's say it's a write operation. We need to write something at an address and put some data there, right? And this will be implemented with some accesses to the server that people call cell probes or probes. And well, we'll do some accesses to the memory on the server. Then the RAM program will answer, right? Like it will do something. Well, if in case it's a write operation, then the data that is returning is empty. You can think about it as empty. Otherwise, if it's read, then it will actually return the memory, right? What is stored on the server, on the location, and will go on like this. Now, right? We'll do it a couple of times, hopefully. Okay. So what do we want from this? Well, we want, right, the original motivation of Goldreich and Ostrovsky was that it's an oblivious RAM. Like the name oblivious is motivated by oblivious Turing machines. So the oblivious RAM should behave independently, optimally, of the input, right? Like it should do the same thing, irrespective of what is the input sequence of the operations. Now, well, what does it mean to do the same thing? Well, the question is, what does the adversarial server see? Well, the server, he sees the type of the operation, right? He sees the address and then the data load. So the data load, people usually think of it as being encrypted. So we just don't think about it at all. Like whatever is stored on the server has no information what is inside. So basically, so far, it would only see the type of operation and the address which is being accessed, right? So the type of operation is not really big of a deal because you can just with constant overhead hide that. Because for any read, right, I could do a dummy write and then read. And for any write, I just do the same. So with very small blow up, you can also hide what is the type of operation that you're currently performing. So the only thing that the server is learning is actually just the sequence of addresses that are being accessed throughout this computation. Okay, so what we want to hide the the input sequence that's being implemented. And how do we do it? Well, we do it by somehow obfuscating the access pattern on the server. Now, more formally, what is the definition of security, of obliviousness that we want here? Well, we want for all input sequences, y prime. So what is the input sequence? It are all the incoming operations that the RAM program is receiving. We want that their statistical distance is small. Okay, here we're proving lower bounds. So actually, I'm using some very lax notion of security, right? I want the statistical difference of the access patterns to be smaller than 1/4. Now there is one thing: you need to pick which input operations are indistinguishable. And this depends on how useful you want the notion of ORAM to be. And if you would require this obliviousness to hold for any like pair of input sequences, then you might end up with something that's not practical at all, right? Like consider an input sequence that is a single operation, and consider an input sequence where you have 100 operations, right? To make the access pattern like indistinguishable, then you need to do some padding, right? So you somehow need to deal with the longest input sequence. So therefore, we restrict ourselves only to pairs of input sequences that have the same length, right? So y and y prime, the input sequences have the same length. Okay, so that's the model. It's basically like the same model as in the Larsen-Nielsen lower bound. Well, okay, so how can we achieve this? Well, there's always the trivial solution. You can achieve ORAM with linear overhead for free. What do you do? For any input operation, you just scan the whole memory, right? Then you're perfectly oblivious because it just doesn't depend on the operation, right? So, like, if you allow me to do n operations for any input, then I'm fine. Well, the issue is that the overhead is huge. And what is the overhead? Well, it's the same as what Casper was defining, right? It's the number of server probes per operation in the amortized sense, right? So if I need to do like m operations in total for a sequence of length n, it's m over n, right?
Well, after you read it once, you can do everything locally.
What's that?
After you read once everything, if you have enough memory to store everything.
Yes, yeah, but in this model, like everything is coming online, right? Like you get an input, you need to process it, and then you cannot come back to it.
You don't
Right.
have a local memory is small.
Exactly.
Yeah. Yes. Yeah, okay. So so that's the bandwidth overhead, and now for the results. So first of all, I have to apologize, right? There's a huge literature on ORAM. So if I'm not citing your paper, it's nothing personal, right? So I just simply couldn't have put all the references there, so I went the simplistic way. And well, we have the foundational paper of Goldreich and Ostrovsky. They actually presented a construction of oblivious RAM. They had like a cubed overhead construction, and well, in terms of lower bounds, well, they showed that in the balls and bins model, where the oblivious RAM cannot manipulate the data, it can just put something into a memory location, then take it out and write it somewhere else, then actually log n bandwidth overhead is inherent. So in terms of upper bounds, we're doing quite well. Since the last year, there's the Asharov et al. Result about Optorama, and we have improved, right, like we as the community have improved the constructions to log n. And in terms of lower bounds, well, there's this weird thing that people realized that actually like these lower bounds for ORM are somehow tricky, because it really depends on the model. Because if you would allow, right, as Tal was saying, the machine to like process everything and then implement, right, like if it would see the input operations like at once, not online, then there we don't expect to prove some meaningful lower bounds, because it would imply lower bounds in circuit complexity. That was the result by Boyle and Naor, and subsequently it was improved by Weiss and Wicks, right, that actually showed that you could get possibly some lower bounds for locally decodable codes. Iftach?
What does it even mean to the machine, the set of operations determined in advance, and the client can see the sequence of operation? How can it be as bound to memory? What does it mean?
I don't know. Okay, it's a model. It's not clear like what it means, but you need to be careful about, right, like your lower bound has to explicitly use the fact that sorry. So your lower bound should use the fact that the algorithm is online, that's processing the input operations one by one. Okay, so like the state of the art after last year crypto was Larsen and Nielsen, and they showed that yeah, actually the log n lower bound is inherent, like in a very general model. even for computational security. And well, there was the caveat that Casper actually mentioned, and it was that the server actually sees which bunch of accesses in the server memory corresponds to what input operation. And okay, so here is the question: like, is this like all that we need, or like should we try to prove a better lower bound? So let's talk about it a bit. Okay, so this is the model of Larsen and Nielsen. Okay, so you have two input sequences, y and y prime. So it's like write, write, read, read, write, write, read, read, and they both correspond to some access patterns. Okay, so the access pattern actually is the same if you would not split split into chunks the operations on the server that correspond to each input operation, right? So the only difference is that for the two reads, in the y we have the block 1, 4, 3, 1, and for the y prime we have 1, 4 and 3, 1. Okay, so in the model of Larsen and Nielsen, the adversarial server sees exactly this, including the separators. And Larsen and Nielsen showed that like this, the fact that the adversary sees the separators between the blocks actually allows you to prove the lower bound, right? Because if you would want to construct an ORAM, right, which is secure against an adversary that has this additional power, right, then it's possibly harder, right, than if you had an adversary that doesn't see the separators. Because, yeah.
But so you know in advance it will be 4 operations? Because if I look at your 2 sequences and I cut them after 3 operations, they're very distinguishable, right?
Yes, yeah.
One extra and one data.
Yeah.
So I
it
thought
is.
the definition of online also meant at any moment you will get a message, okay, sequence is over. You say no, I know in advance there will be n operations, I just don't know what they are.
So the model of Larsen and Nielsen actually assumes that you know the length of the sequence, right? The distinguisher you want like for any n, and yeah. So you know the number of operations, you just don't know the particular operations in the sequence. So okay, first of all, yeah. Yeah. Okay. So. Yes. Yeah. So perfect, right? Like confusion happened, so it's my fault. Let's resolve it. So you have operation write at location 1, data 1, right? So this is what the client receives, and now he needs to implement it on the server. What's going to happen on the server, right? The memory locations 1, 2, and 4 will be accessed. So this is what the adversarial server sees, right? So yeah. So this is the access pattern that's derived by the ORAM from the input sequence. Yeah. So okay. So first of all, the Larsen-Nielsen lower bound applies to all known constructions of ORAMs, and that's because like the known constructions are very systematic. What does this mean is that you as an adversary, you have a very good estimate for how many operations on the server will happen for any input operation. It's like extremely structured, and therefore like the lower bound applies to it. But still, right, now interpreting lower bound as like a guiding template for designing algorithms, I should ask myself, okay, so if this is the thing and all the constructions have this structure, can I actually hope for building more efficient ORAM, right, by playing with the separators? I could try to, you know, like obfuscate the boundaries, and then maybe this is exactly what allows me to get the efficient ORAM, right? And we show that this is not the case. I should click faster, I guess, because this is dying on me.
We can do it for you next time.
Okay.
Yes, I was asking what happens after 3 operations?
Yep.
I assume you try to obfuscate those things. So what do you report after 3 operations? So I understand that after 4 operations you will report the thing without delimiters.
Yeah.
What do you report after 3 operations?
After 3 operations, well, you would see, right, like this and that.
So essentially delimiters are for free inherent in the model then?
Yeah.
Unless you separate it
Okay, so now to the model. Okay, so one thing that I should point out is, well, the next slide. Well, the original model of Goldreich and Ostrovsky had no separators. And somehow it feels that the separators are introduced by Kasper and Jesper because of their proof technique. Because they took technique for proving lower bounds for data structures in the cell probe model, and you know, like it was natural to, right, like because how you're building this tree, you need the separators, so that's what you do, and it turned out that what you get is actually applicable to all the known constructions. But the original model says, well, you know, like the only thing that the adversary sees is the whole sequence after the fact, and we want to build an ORAM that is secure against this adversary. So in particular, this adversary has much less power, right? Because he sees only the whole sequence in the end, right? He's not using the fact what is the timing between the accesses. Then it might be much easier to build an ORAM against such adversary, right? And our work shows that, even against such weak adversary, you cannot succeed. You need to have the log n lower bound. So yes, so that's like what we do in this work. Well, we show an omega log n lower bound for statistical security. I will talk about the particularities of the computational model in a sec. And we are, of course, proving something for online ORAM because we don't want to prove well, it's not that we don't want to, but we are not that ambitious. We don't want to prove circuit size lower bounds. And we do it in the rather generic model without separators. So what is the take-home message? What we're saying is that, well, it's totally OK to concentrate on constructions of ORAMs that are very structured, right? The fact that people did it in this way is justified because it doesn't help you to do something crazy, to play with the separators. So that's, you know, what, yeah.
Can I ask you something about the existing upper bounds? There, they also really need to know the length of the sequence in advance, or they can stop at any moment, right? You get a query, you do something,
no,
be told this is the end.
It's totally online. What I'm saying is that the fact that the adversary knows a priori what will be the number of accesses for a given single input operation, that's totally fine, right? So that's the point that I'm making. They certainly don't need to know the length of the sequence. Okay, so how do we prove it, right? So we basically, what we do, we take the information transfer technique from Domain and Patrashku, and we adapt it to this cryptographic setting. We extend it. Before, Kasper and Jesper, they build this tree. So our idea is that, well, if we don't know the limiters between the blocks, then we need to deal with it somehow. But all the information is already in the access pattern. That's our observation that whatever you need for the lower bound, it's already there. You don't need this delimiters. So we come up with the notion of access graph. If you are given as a server some access sequence, so you can build from this directed graph in the following way. So the vertices will correspond to the probes into the server memory, and there's going to be a directed edge between subsequent probes to the same memory cell. Okay, so let's look at it. This is what the adversary sees, right? He sees the access pattern. It's just the we're accessing 1, 2, 4, 3, 5, 1, 4, 3, 1, and now we will join them by edges. So 1 has been accessed only at this point later. And, well, 2 has not been accessed afterwards. 4 has been accessed here. 3 here. 5, we didn't access it afterwards. And then there was one more edge for 1. So our graph is a collection of directed paths. And what we argue is that this access graph of computation induced by an oblivious RAM has to be dense. So, I mean, dense here means if I have a lot of edges, right, it means that I have a lot of accesses to the memory, and therefore I will have a large bandwidth overhead. So what is the notion of denseness that we use? We talk about L-dense K partitions. So a K partition is just a partition of the vertex set into some subsequent pairs. Okay, so this is a one partition. I have like one pair of like subsequent vertices. A K partition, like a two partition, would be I would have like two pairs, right, and so on. And it's L dense if there are edges that go between these two consecutive blocks. I need at least L edges. So this is a one partition which is 3 dense. I have 3 edges across. And right, like after seeing the talk of Casper, we're going towards the information transfer technique. I want to argue, right, I will try to build a sequence where I will have a lot of these edges and where like it will somehow correspond to the fact that later I need to read from some location where I wrote some random data and use an incompressibility argument similar to the information transfer. So, okay, let's give you the proof idea. The proof idea is very similar, but now we're using the L-dense K partitions. So first of all, this is great if you look at the proof. Simply by the correctness of the data structure, here in the case of oblivious RAM, you get that there is one sequence that needs to have a lot of edges. So that was the random writes and reads, right? So if I have like random, write random data, read it, write random data and read it. So because like I'm always rewriting, I cannot later remember a lot, so I need to ask a lot of queries right about locations that were written here. So simply just by the correctness of the construction, you get that like for all K's, there is some sequence where you will have like n over 5k dense K partition with high probability. Okay, like yeah. Yeah. So this is a 4 partition, right? I have like 1, 2, 3, 4 pairs of consecutive blocks. And it's 3 dense because between each pair I have at least 3 edges. Yeah, so this is the notion of partition. So, the correctness gives me this, that like there is always a sequence that has this dense K partition property. And then by security, right, this is the obliviousness. You shouldn't be able to distinguish the access patterns, in particular the access graphs that are easy to derive from the access pattern between like different queries. So you can translate the 3 dense 4 partition property to your favorite access sequence. Like Jesper and Casper, they had this dummy sequence of write zeros and read from the 0 location. Actually, right, the obliviousness property is very generic, so you can show this for any arbitrary sequence. Okay, so then we just repeat this. We did it for like 3 dense 4 partitions, so we can do it for 5 dense 2 partitions, and you see like all these edges will get absorbed into one particular sequence, and by some simple lemma, we show that if you are like dense partitioned for many of these values for density and partition, then you actually have a lot of edges. And this is going to show that the access graph of the like one arbitrary sequence has at least n log n edges. And we like derived the access graph from the access pattern, right? So then just by the definition of the access graph, we get the bandwidth overhead bound that we wanted. So, okay, I'm not finished yet, but I will like spoil the open problem session. I want to give the open problems right away. So there's a couple of them, like some are actually very foundational. The first thing is, how is it with definitions of ORAM? Okay, so in the literature, people considered many different definitions of ORAM, and some of them are more meaningful for proving a lower bound than others. And like the question is, like, if all the constructions that we have in the literature, like match the model for which we're proving a lower bound. I didn't go through like all of them, so like my best guess is that yes, like for all the reasonable models that are there, we are proving the lower bound. One interesting thing that wasn't, to my knowledge, pointed out in the literature, at least I didn't find it anywhere, is that like the original definition of Goldreich and Ostrovsky has an issue, like a technical issue, which allows you to satisfy it like with no security, with constant overhead. So, Yuval, how much time do I have? 4 minutes. Okay, so maybe I concentrate on this. So there's another thing, and that's the results of us and Larsen and Nielsen apply to computational security, but to like very carefully defined notion of computational security. And we actually distinguish between strong computational security and weak computational security. For the weak one, we get only super like linear lower bound for the length of the access pattern, and it would be very interesting to show whether you can prove actually the log n lower bound for the bandwidth overhead even for the weak notion of computational security, right? Like weak notion, possibly easier to construct, so harder to prove lower bounds. Yep.
I'm a little bit confused. The R construction with omega 1, with O1 overhead in the computation model. Is it long records or what is the...
So I'm not sure what you're exactly referring to. I know of some works that do this trick, that they outsource some computation of the RAM machine to the server, and then you can get below the...
so if the server is allowed to do computation...
Yeah, then you can actually do some things. But you will possibly need like some advanced crypto for that. So
I think nowadays the assumption of one function was very...
yeah, maybe, but...
so your model, the model that we have below one for computation doesn't allow the server to do...
No. He cannot do computation on behalf of the RAM machine. Okay, so I'm gonna skip the computational security. It's in the paper, or talk to me after, in one of the breaks. So here is the issue with Goldreich and Ostrovsky, and if you actually have it in some paper of yours, please, like come to me, and I would be happy to attribute it correctly to whoever found it first. So what they want is different from the definition that I actually showed you. What they want is that if the distributions of the length of the access patterns are identical, then the accesses themselves have to be identical. So this is different, right? Because what I wanted was that if the input sequences had the same length, then you had to have indistinguishability of the access sequences. So here it's different. And in particular, notice that if the length of the access patterns are different, then no security is needed. And this is exactly the loophole that we use to bypass it, right? Because then you can just build an ORAM with no security that basically just encodes the input sequence into the length of the distribution, making sure that any input sequence has different distribution of the length of the accesses, and therefore you don't need any security, okay? So let me give you the upper bound, okay? So here I am presenting a constant overhead Goldreich-Ostrovsky ORAM, okay? So what does the ORAM do? So for line number 1, don't do this at home, right? So perform each operation from Y directly on the server. After this, we're done, no security, okay? So I failed already. So 2, then just do some dummy reads from address 1 and do as many of them as is the length of the sequence. And afterwards, to code the input sequence, just pick a random R that has the same length as Y and compare it to the input sequence. If it is smaller, then do just one additional read. If it's larger, then don't, right? This will make sure that we're actually coding the Y into the length of the access sequence. What is nice, right? Like I'm extremely efficient. Bandwidth overhead is at most 3, right? So I'm doing like 2 or 3 operations. Now, you could complain to me and say, well, the distributions of the length of the access sequences are only like statistically apart. They're actually like negligibly close for some pairs. But we played with it because we wanted to get better security. So we have similar dummy construction of an ORAM where you can make the statistical distance even noticeable, like 1 over n times m, where m is the size of the memory that you're allocating. So like even if you would require the Goldreich-Ostrovsky security notion for sequences that are not just identical, but like reasonably close, then the definition is You can satisfy the definition with constant overhead. So that's, yeah.
I have two quick questions. First, your dummy upper bound is balls and bins, right?
Yes.
So that you can pinpoint the error and their proof of lower bounds, balls and bins?
Mm.
That's one. And my second question, you think maybe they just had a typo and they didn't mean if length of A equals length of A prime, but instead if length of sequence equals length of sequence prime?
I don't think so, because they use it consistently throughout the paper. So, and it's used like in some other papers in the literature. So, yeah, like there was, you know, I think that there's at least some confusion. So you just want to like point this out, that you need to be careful, right? Like, I mean, why did we find this? Because we tried to prove a lower bound and we failed, right? So you see that
They succeeded, so they had a bug.
yeah, possibly. I mean, if you would use the reasonable definition with their proof, it's going to go through. That's, you know, like how it is. What? No, so like it's not really a typo because.
Why would you put condition on the ciphertext in order to guarantee distinctibility? Does that make sense?
Yeah, I agree with you, but they do it, you know, like.
Regardless of the, you know,
Yeah.
the fact that you can implement it easily, it doesn't make sense as something to require. Right? It's not a reasonable requirement.
Well, it somehow makes sense, right? Like you could see it again through like to bypass the padding issue. That if you blow up the length at the the input sequence to like similar length of excesses, I don't know.
Assume each real query takes a specific number of probes. That was their assumption. And then the definitions are equivalent.
No, so like we
And that's
didn't.
my theory.
Yeah. Okay. So, but just okay. Yeah. So basically, that's all that I have. And if you want the papers online, and you know, I can talk to you if you want to know more.
Okay, so any more questions since we have one last question?
The correct definition has to just remove that if.
No. So you just need to consider like input sequences of the same length. I mean, it's.
Instead of assuming the output to be equal, we should assume that the input sequences are equal length and we want the output distribution.
Yes, yeah. So this is a definition. I don't know how meaningful is it to practitioners. So just to put it like, actually I need to do one more disclaimer. So there is a work by Haider et al. From 2017 that we discovered after our work, and they noticed this issue. It's just that like their dummy ORAM has exponential overhead, and therefore like it's not really that interesting because you can get like ORAM with linear overhead for free. So yeah. But I guess my time is up.
Okay, thanks.